All right, so this is Horner again, and we're going to look at the last section in induced currents, and this is on motional EMF. This is part 8, and so what we can do is we can say that if I have a bar, and let's just set this up. Let's say that I have some sort of power source here, and I hook that up to a bar, then I would have a little bit of current flowing in here. And if I take a magnetic field, for example, let's just say that there's one going into the page, and I change that magnetic field, then what I can actually do when I turn on that electricity, it will then make this bar shoot off this way. So this is what we call a rail gun. The military is using these more and more because they're pretty inexpensive and you don't need to use any gunpowder. Makes it really kind of nice. But anyway, let's go back to motional EMF here. We know that the potential that I get is equal to BL times V, where B is magnetic field, L is the length of that bar, and V is the speed of the bar moving through the field. The bar has to cut through the magnetic field line, so I'll show you that. It can't be moving parallel, it's got to be moving perpendicular to it, and you can easily derive this from Faraday's law of induction, which we just did. So here is Faraday's law. We just said it's the change in flux over the change in time. Usually there's an N number there, but we're not going to have it here. We're going to assume that we just have a coil of 1. If I know that the cosine of the angle is equal to 1, we can get rid of the cosine part. And so we just have the change in the magnetic field times the area. Area is length times width for a box. So we're going to have a box-like structure in all of these where we have our setup, and that's just divided by the change in time. We know that the change in position over the change in time then is velocity. So that's where this equation comes from. All right, so here we go. Let's take a look at our first thing. On this one, instead of having a battery right here, we have a resistor, which means that if I actually take a string maybe and tie it to this, and then I pull this in this direction, I can actually create some current within this loop because I have a resistor. And notice now, instead of changing the magnetic field, I'm changing the area. So if you remember BA, and we usually were changing B, now we're going to be changing the area. When I change the area, then that will give me an induced EMF, as long as I have that over a period of time. So the very first thing they want us to do is how much current flows through the resistor. So let's use our equation that we just learned, which is the potential is equal to B times L times the velocity. We know that the change in voltage is equal to IR also, and so here we're going to say I is equal to the change in voltage all over the resistance. Our change of potential we just said is the same as EMF, so that's B LV all over R. Now what we'll do is we'll put a little tail on this V so we don't think it's voltage. We want it to be velocity. So this is equal to 0.15 Tesla. Notice the field is not changing now. The thing that we're changing is the area. So we're going to take that times 0.5 and then multiply that times our 2 meters per second. We're going to then go ahead and divide that by 3 ohms. If you go through and do your math, you're going to get 0.05 amps, and that is the current. But they want to know the power, and we know that power then is equal to a lot of things. We could do IV, we could do V squared over R, but let's just do I squared times R since we just solved for current. So this is 0.05 squared, and we're going to multiply that times our resistance, which is 3 ohms. When we get done, we're going to end up with a value of 0.0075 watts. So this setup, if I'm moving this bar to the right, will create some current flowing through, and when it does that, it will then also provide power in that system. The next part of this, they want us to go through and try to figure out in which direction is the induced current through the resistor. Okay, so if we think about this one, we're going to have to go through and we want to know which direction is the current flowing. So I'm going to take my hand, I'm going to put my thumb in the direction of this X, okay, so that would be into the page. If I put my thumb into the page and this wire is moving this way, we'll notice that the magnetic field is getting bigger. So here, I know the area is getting bigger, but our magnetic field is also going to be getting bigger because there's going to be more of these X's on the inside. So when this bar moves over here, you'll notice I've got a whole nother row of X's. If that's correct and that field is increasing, I need to point my thumb now towards me. And when I point my thumb towards me, because that is now the induced magnetic field, we'll see that the current is flowing in that direction, which means it is going to travel down through that resistor. If this box was getting smaller, then the magnetic field would decrease and the current would go in the opposite direction, because my thumb, then my induced magnetic field would have to point in the same direction because it's getting smaller. So remember, anytime you increase magnetic field, either by just increasing the field itself or increasing the area, then you will have an increasing magnetic field that's induced in the opposite direction. And if I have a decreasing magnetic field, I will then have an induced magnetic field that is increasing in the same direction. So we kind of did that a little bit earlier. Very last problem is one that's still very similar. It says assume that the rod is being pulled so that it's traveling at a constant 2 meters per second. They want to know how much force must be applied to keep it moving at this speed, which essentially means if I'm applying a force in this direction, then there's got to be a force of magnetism. So we're going to say FB that is going in the opposite direction. So let's go through and put everything in. And we know that our current here is equal to 0.05 amps. That's what we just did. And we need to use the force equation for the magnetic field along this wire. So here we've got F is equal to ILB. Our current is 0.05 amps. We know that the length that we're working with here is this 50 centimeters, which would be 0.5 meters, and then we have a magnetic field of 0.15 Tesla. And so here we find out that our magnetic force then is equal to 0.00375 newtons. And that is the end of motional EMF.